Hey, what's up, physics peeps? It's Mr. Scott here. Day 30 of quarantine. Hopefully you're doing okay. We are going to try and recap practice file 8.3, and hopefully by this point you've already done the practice file and entered it as a Socrative, so that way your physics teacher still likes you. So hopefully by now you've already gotten your instant feedback on Socrative. We just want to make sure that you understand why the light ray is doing what it's doing. So here we're going from air to water, which is like what you did in your simulated lab. And we always say bring out your wheels, right? So like you saw on the refraction demo vid from Mr. Sarzak, the wheels, you can just trace them down. If you just imagined like two wheels over here, and as they came in, the medium change, this bottom wheel is going to hit first. And because of that, it's going to have to turn the bottom wheel while the top wheel is still moving at the same speed that it would be moving while the light ray was traveling in air. So the wheels then would be moving different speeds until this bottom wheel keeps on getting and turning until eventually we have both wheels in the new medium going the same speed, and then they'll continue on in the path that they were going originally. Now you can either just like memorize this, or you can try and like use your wheels every time, but every single time we go from an index refraction that's smaller, where air is n equals 1 and water is n equals 1.33, you're always going to bend towards the normal line and have an angle of refraction that's smaller than the angle of incidence. And if we flip-flop the index of refraction, you do the exact opposite, where you'd bend away from the normal line. So this is called the least time principle, and you're going to learn more about this tomorrow. But essentially, like, the light ray wants to take the least amount of time to get from one place to another, so it's always going to spend less time in a more dense medium and therefore take a smaller path to get down to the new medium change after that. So C is your correct answer. Let's try number 2. All right, for number 2, we're going from glass to air, and we flip-flop the medium. So that way the first medium is going to be a higher index of refraction. Glass is typically about 1.4 to 1.6 for its n value, and then air is still about n equals 1. So that bottom wheel now is going to hit the medium change first, and it's going to speed up because it has to go faster in air than it does in glass, which means we're going to turn and bend away from the normal line, and path A is your correct choice here for number 2. So number 3 looks a lot like number 1, where we're going to bend towards the normal line, but what they're trying to show you here is that when it comes back out and goes from glass back into air, we should be able to come back out parallel to the original light ray. So why does the straw look bent when it's in a cup full of water? Because that light ray is slowing down as it goes from air to glass and bending by that angle and coming back to your eye just slightly off and displaced from the original light ray, which would have been path B, but instead in reality it's actually at A now. And number 4 looks a lot like number 2. So we flip-flop the index of refraction and go from a higher index of 1.33 to 1, and we bend away from the normal line and speed up as we go into air, and now path C is correct. All right, so question 5 is a bit of a thinker, and here you can see there's a lot going on, but we're telling you up at the top, the speed of light in the left block is greater than the speed of light in the right block. So what that means is that we have to be going faster in the left block than we are in the right block. What that also means is that the index of refraction of the right block has to be greater than the index of refraction of the left block. And if we're slowing down more, we have to be bending and creating a bigger drastic change in the angle when we emerge and come back out on the other side. All right, so to the best of my abilities, I tried to make a drawing here of where the light ray would be if there was no speed change, which is that dashed line that goes straight through the block. And then I've also shown the normal line and that we're more displaced on the block on the right than we are on the block on the left. So let's apply that here to number 8 with Mr. Sarzak, who is being roughed up here by quarantine. But you can see that he's got goggles on, and if we wear goggles, that allows us to have an air pocket in front of our eye and allows us to bend the light ray like it normally would going back to our retina. Now, a fish would do the exact opposite because they've evolved underwater, so they'd probably want goggles with water pockets in there so that way they could still see. And yeah, it'll be displaced a little bit due to refraction, but at least they can see the image more clearly. All right, so number 6 is where we really get fun. We have to notice here that we're starting out in air with the light ray, and we're going to change into glass, then plastic, back into air, back into plastic, back into glass, and then back to air one last time. And we've put over here on the right something pretty important, and that's the velocity of the light ray that would be going in each one of the mediums. And notice that up here at the top we have V equals C. So C stands for the speed of light. E equals mc squared, if you remember that equation from special relativity when we talked about Einstein. So that c is going to be how fast light can go at a maximum, which is roughly 3 times 10 to the 8th meters per second. But then as we change mediums, we know we slow down because that's what refraction is. And we go to 0.6 or 60% the speed of light when we go to glass, 0.7, 70% the speed of light in plastic, back to the speed of light in air, and then we do a few more medium changes after that. But what we really want you to see in this problem is the symmetry that gets created when you start drawing the light ray. And at the end of the practice file, we'll do all the calculations with Snell's law, exactly what angles it should be like bending at as it goes through all these medium changes. But for now, we'd ask you to just do a rough sketch and be able to see that it should be coming out back into the air at 50 degrees. So after you use your wheels, here should be our finished product of which way the light ray is bending. And you can see we bend towards the normal line when we go into the glass, a little bit back away from the normal line in plastic, and then a lot away from the normal line back into air. But that air angle is still going to be 50 degrees because it's going to come back out parallel, just like it did in numbers 1 through 5. On to number 7, where we give you a practical example of how a light ray goes through your eyeball to get back to the retina and then pass a signal to your brain. And things you probably didn't know, your eye is 99% water, which means that as we go from air to water, we're bending towards the normal line from any light ray that goes into the top of your lens of your eye or the bottom, and we get a nice little focal point right back there on the retina. Now, if you go from water to your eye, that's not much of a medium change, and there'd be a very slight bend, but these light rays are going to come back to your retina in 2 different locations. And that means you're not going to see much. You're going to see a very big blur that gets passed to your brain. All right, so on to the part that you may or may not still be drooling about. Let's try to figure out what the index of refraction actually is for air, glass, and plastic. And then let's try to figure out what these angles from the rough path that we drew for the light ray actually are using Snell's law. So whenever you want to calculate the index of refraction, it's actually pretty simple. It's just a ratio of how fast the speed of light is compared to the fraction of the speed of light, which we're going to represent with an x here, that it can go in the material that it's currently in. So when we represent this, we call it n equals c over xc, but you'll notice that anytime you have a speed of light c on top and a speed of light on bottom, that's going to cancel out and you're going to get a simplified expression of 1 over x. And for air, that's pretty easy because it's going the speed of light, like I said, roughly. So we can just plug in 1 for the x, and you just get an index refraction of 1. And for glass, you'd end up plugging in 0.6. For plastic, you'd end up plugging in 0.7 and getting other values that I'll show you right now. So as we'd expect, glass has a higher index refraction because the light ray is only going 60% the speed of light, and it's more dense than the plastic. And then the air is the least dense thing, where it's going roughly the speed of light at 3 times 10 to the 8th meters per second. And last but not least, let's try and get some practice with Snell's law so we can actually calculate these angles that the light ray is coming out into new mediums at. And remember that Snell's law, whatever is on the left side of the equation is the medium that it starts out in. So that's going to be your n1 sine of theta 1. And then whatever it goes into is going to be your n2 sine of theta 2 on the right side of the equation. So try to keep it simple. You may end up flip-flopping sides of the equation as we go through, but we should notice that the angles tend to be equal depending on what medium it's in. Here's the work setup for Snell's law using n equals 1 as the first medium and n equals 2 being 1.7. And you can see here that we have to use the inverse sine to both sides, just like we did in the first semester when we were working with projectiles. And we're going to end up with an angle that's 26.8 degrees. If you got something weird that was negative or under 1, you probably are in radians, and remember to switch over your calculator. So now the light ray is in glass and it's going to go to plastic. So as it does so, you can see we can use alternate interior angles to represent our theta 1 now is 26.8 degrees. We're going to solve for what we labeled here as theta 3 for the third angle, because it's the third medium that's going into. And in order to show you work for this, same exact setup, you're just going to flip-flop the angles and the index of refraction, so that way n equals 1.7 is n, the first index, and then 26.8 degrees is now your first angle. So you can see here we did the work and it ends up being 33.2 degrees for your angle in plastic. And hopefully by this point you're starting to see some symmetry and know that every time we do this, the angle that's going to come back out to in air, since it's parallel to the angle it was at the very top, should end up being 50 degrees. But just to prove it one last time, here's the work on how we calculate using now the first angle as 33.2 and the first medium as 1.4, going into the second medium of n equals 1 and solving for that second angle. And as you hopefully expected, it comes out to about 50 degrees for the air angle. Like I said, we could do Snell's law over and over again. We could do it 3 more times, but the work's going to be the same. And those angles that it comes into the new medium at should be the same ones as we did at the top, because they have to be parallel going into that new medium. They just get displaced due to the fact that refraction happened. All right, and that'll do it for this screencast. So hopefully you're getting it. If not, make sure you use those Google Hangout meetings that we now have, and we'll talk to you soon.